In this lesson, we will discuss the process of natural radioactivity. Now, what does radio means? Radio has something to do with radiation. So obviously the process of radioactivity is the process of emitting radiation. Now, what kind of radiations? We talked about electromagnetic radiations in about a couple of lessons ago. I'm sure you have now a clear picture of what electromagnetic radiations are. At the long wavelength region, you have the radio waves, then the infrared, the visible light, the ultraviolet, X-rays, gamma rays. They're all differing frequencies and energy values of electromagnetic radiations. There can be other types of radiations. Now, in this lesson, we are going to look at radiations that are thrown out or emitted by atoms or elements that are unstable. Now, what is an element that is unstable? The picture of the atom that we have evolved, that we came up with in the last couple of lessons, is we have the nucleus of the atom that contains protons and neutrons, and of course surrounded by electrons, and we spend a considerable amount of time describing that model of the atom. Now, in this lesson, we are only concerned with the nucleus. Radioactivity is a nuclear process, something that happens inside the nucleus. So we are not worried about the electron structure outside the nucleus. Now, we know that protons are positively charged particles. When you put a large number of these positively charged particles together, can you create stability inside the nucleus? Is it possible to hold them together peacefully so that you have the nucleus of a stable element? Well, sometimes it is possible, sometimes it is not. It depends on the combinations of neutrons and protons. In fact, the combination of these neutrons and protons is what actually creates the stability. Now, some combinations of neutrons and protons may not be conducive to stability. Some others may produce stability. So, what is an unstable nucleus? Now, atoms with too many neutrons or not quite enough can sometimes exist for a while, but they are unstable. Now, if a nucleus is unstable, it has to throw away a part of it to achieve stability. And that's what we're going to discuss in here. Now, all the elements beyond bismuth, that is atomic number 83, are unstable. They have too many neutrons. So if there are too many neutrons, that will create instability. So all the elements beyond bismuth are unstable. And unstable nuclei or unstable atoms are radioactive. These nuclei change or decay. They decay by throwing out radiations. And what are these radiations? These radiations may be made of particles, or they may be just electromagnetic radiations, just energy. Now, throwing out particles or energy can result in stability. Just like if you have a group of people and there are two people creating trouble there, we can chuck them out, right, to create stability within that group. Now, radioactivity is the spontaneous emission of particles or energy from an atomic nucleus in order to create stability. Now, you are familiar with the picture of the nucleus that contains protons and neutrons. If you throw away nuclear particles, then obviously the identity of that nucleus will change. If some nuclear particles are thrown out, the remaining nucleus will be the nucleus of some other element. That means the emitting of these radiations will result in the changing of the identity of the element. All these things are possible in this case. So let's start by discussing how was radioactivity discovered. Like many other scientific discoveries, the discovery of radioactivity actually happened by some accident. Now, what kind of accident did happen that led to the discovery of radioactivity? The radioactivity was discovered by a scientist called Becquerel. Now, Becquerel was experimenting with a sample of uranium salt, and for his experiment he needed sunlight, because he exposed the uranium salt to sunlight and he was studying the property of that material. And one day it so happened that it was cloudy and there was no sunlight, so he wrapped this material in a photographic plate. Now, don't ask me why he did that. And he kept it away in a drawer or someplace. And of course, he looked at the photographic plate later. So he put his wrapped photographic plates in a darkened drawer along with some crystals containing uranium. Now, when he developed the photographic plates, much to his surprise, it was noticed that the photographic plates were exposed. These plates were kept away in a dark corner. Now, if these plates were to be exposed, that means some radiation must have fallen on it. Now, if some radiation has fallen on these photographic plates, where did these radiations come from? The only source for these radiations to come from is this uranium salt. Well, the emanations did not require the presence of initiating energy source. So obviously means that these radiations or emanations that came from the uranium salt did not need any initiating source like the sunlight or heating or electric discharge or any such initiating source. It happened spontaneously. Well, the emanations actually did not require the presence of an initiating energy source. Now, later, Becquerel demonstrated that these emanations were actually emitted by uranium and shared certain characteristics of some of the radiations that we are familiar with, like X-rays or gamma rays. Some of the radiations that were emitted by this material were actually similar to the electromagnetic radiations that we are familiar with. That means these radiations actually contain some electromagnetic radiations. Now, working in the Becquerel lab, there were two very special people, Marie and Pierre Curie, and they became very involved in the study of radioactivity. Now, I think I have a picture of Mary here and Pierre over to the other side, working in her lab. Now, after working with radioactivity for some time, Marie Curie wrote, "The subject seemed to us very attractive, and all the more so because the question was essentially a new one. We didn't know anything about these things before. It was a very new branch of science, and nobody knew anything about it so far, and nothing was written on it so far." And Marie Curie devoted practically all her life in the study of radioactivity. Now, she is best known as the discoverer of the radioactive elements polonium and radium. And she is the first person, in fact the first scientist, who received 2 Nobel Prizes, one in chemistry and one in physics. And most of her work is based on the process of radioactivity. Now, once you have made a discovery like this, that a material emits radiation spontaneously? Well, obviously, it is a question you ask, what are these radiations made of? So Becquerel analyzed these radiations. Now, what do you do to analyze such a radiation? Here I have a simple experimental setup that Becquerel used. Now, this is a magnet. That means in the region between the pole pieces of the magnet, there is very strong magnetic field. So the first thing Becquerel did was to subject these radiations to a magnetic field. Why? Why did he do that? Well, we know that electrically charged particles, when subjected to a magnetic field, will experience a force and they will move. Is that right? Now, a positively charged particle will experience a force in one direction. Negatively charged particles will experience a force in the other direction. Now, look at the result of the experiment. Of course, Becquerel had detecting devices all around this setup. Now, he found that the radiations emitted consisted of 3 different types of radiations. One radiation was deviated to the right, another radiation was deviated to the left, and the third type of radiation did not suffer any deviations at all. Well, that means if the radiation that is deviated to the right has positive charges, then the radiation that is deflected to the left must be carrying negative charges. And then what is this radiation that was not affected by the magnetic field at all? It must not be carrying any electric charge, or it could be simple electromagnetic radiations. So he identified 3 types of radiations as a result of an experiment like this. Now, one of them consists of massive positively charged particles. Now, how do you know they are massive? If you look at this picture, these particles deflected to the right did not suffer as much deviation as the particles on the left. Now, that suggests that these particles may be massive because they did not suffer a lot of deviation, whereas these particles that deflected to the left may be less massive. So one of the radiations Becquerel found are made up of massive particles, and they carry positive electric charge. A second type consisted of negatively charged particles, and they are less massive. A third type of radiation was not affected by the magnetic field, and they were found to be very high energy electromagnetic radiations. Now, give me some very high energy electromagnetic radiations. Give me the names of a couple of those. Well, very high energy electromagnetic radiations are X-rays and gamma rays. In fact, these radiations emitted as a result of radioactivity are actually gamma radiations. Now, you have these 3 types of radiations. Becquerel simply named them alpha, beta, and gamma radiations. Just like we call things we don't know much A, B, C, or X, Y, Z, these radiations were called alpha, beta, and gamma radiations. Now look at this picture. Alpha radiations are massive. They are actually part of the nucleus. Part of the nucleus breaks and gets thrown out. And there is a net positive charge. Beta radiations are very light particles. And gamma radiations are simply packets of very high energy photons, which are gamma rays. All right. Further studies showed that alpha radiations consist of 2 protons and 2 neutrons. So, when an alpha radiation goes out of a nucleus, that nucleus loses 2 protons and 2 neutrons. Now remember, a nucleus is identified by its atomic number and mass number. Atomic number is the number of protons, and mass number is the number of protons and neutrons. Therefore, if 2 protons and 2 neutrons are thrown out, it means the atomic number of the remaining nucleus will be 2 less than the atomic number of the original nucleus, and the mass number will be 4 units less than the mass number of the original nucleus. Or alpha particles are simply helium nuclei. Helium contains 2 protons and 2 neutrons in its nucleus. That means an alpha particle is nothing but a helium nucleus. So, if an original nucleus, a radioactive nucleus, emits an alpha contains 2 protons and 2 neutrons, what is remaining? What is remaining will be the nucleus of a different element with atomic number 2 units less. So when the nucleus of an element of atomic number Z emits alpha particle, it loses 2 protons and 2 neutrons, with the result that the remaining nucleus will have an atomic number Z minus 2 and a mass number A minus 4. Very important to know that a radioactive element transforms into another element as a result of an alpha emission. For example, plutonium 94-239. Plutonium has an atomic number 94 and a mass number 239, emits an alpha particle and becomes an element of, becomes a nucleus of element with atomic number 94 minus 2. And what is that element? That element is uranium. Uranium has an atomic number 92. So when plutonium 239 emits an alpha particle, what is left behind is the nucleus of uranium 235. You can see, as a result of the alpha emission, the plutonium element is transformed into uranium element. An important information. Now here I have an animation of that. This is plutonium 239. It emits an alpha. What is remaining is uranium 232. Look at that again. Plutonium emits an alpha, leaving behind uranium 235. Now that is the spontaneous alpha decay. We call it the spontaneous alpha decay. In addition to the alpha, also gamma radiations are emitted. Now gamma radiation will be part of any other radiation. Alright, so we have this radiation equation. Look at this. Plutonium 94-239 emits an alpha, leaving behind uranium 92-235. You must be able to write equations like this representing a reaction. And uranium 92-238 emits another alpha, becomes a nucleus of thorium 90-234, and so on. Another example. Radium, what's the atomic number for radium? 88. Now radium 88-226 emits an alpha, and it becomes the nucleus of radon 86-222. Can you write that equation? Well, here is a picture of that process. There are 2 processes pictured here. One is an alpha particle that carries an energy of 4.6 million electron volts. What is a million electron volts? an electron volt is the energy acquired by an electron when it is accelerated by a potential difference of 1 volt. A million electron volt is the energy acquired by one electron when it is accelerated by 1,000,000 volt. Now, the energy of this alpha particle that comes out of the radium carries 4.6 million electron volt, and it is also accompanied by a gamma radiation which carries 0.186 million electron volt. And so the total energy that is taken away from that nucleus is the sum of these two. This is one possibility. Another possibility is an alpha radiation which carries all that energy, that has 4.745 million electron volt. So these are two possible ways radium degenerates into radon after emitting either only an alpha or an alpha followed by a gamma. So those are two possibilities of the decay of radium-226. And look at the equation for that. Radium-88-226 emits an alpha, leaving behind radon-86-222. How about beta radiations? Now, I want you to look at this and tell me, is there anything wrong there? Beta radiations are very light particle, we said, and it was deflected in the opposite direction. Well, if alpha radiations carried a positive charge, then beta radiation should be carrying a negative charge. They are light particles, and there's only one light negative particle that we are familiar with. They are electrons. So, obviously, it is easy to conclude that beta radiations consist of fast-moving electrons. What's the problem here? The problem is, I started by saying that radioactivity is a nuclear phenomenon. Didn't I say that we will forget about the electrons outside the nucleus? We will only look at the nucleus in order to study radioactivity. Radioactivity is a nuclear phenomenon. That means the radiations are coming from the nucleus. Now, is there an electron or are there electrons inside the nucleus? Well, I want you to follow this carefully. What is a beta radiation? A beta radiation is an electron coming from the nucleus. That is something that is not understandable. Is that right? Radiations are emitted from the nucleus. Can a nucleus give out an electron? What happens is, inside the nucleus, the proton and neutron not always remain as proton and neutron. You see, a neutron doesn't remain as a neutron forever. It changes identity. A neutron can split into a proton and an electron. You see, the charge carried by a proton and the charge carried by an electron are equal and opposite. When you put them together, they are neutral. And when they separate, you have positive and negative charges. So, inside the nucleus, a neutron can degenerate into a proton and an electron. Now, when that happens, the proton will stay back in the nucleus and the electron is given out as the as the beta radiation. Now, neutron has no charge. Look at the symbol for that, N01. It has no charge, but mass number is 1. Splits into a proton, 1, 1, plus the electron that carries a negative charge. So the negative and the positive charge put together is the 0 charge. A neutron inside a nucleus splits into a proton and an electron, the electron gets emitted. Now that means an important change has now happened to the nucleus. What is that important change? In place of a neutron, now you have a proton. Now, when you have an additional proton, the atomic number will increase by 1. So, as a result of a beta emission, the atomic number of the remaining nucleus is 1 unit greater than the atomic number of the original element. That means you have now gone one step higher. Look at this. If you can make an element beta active, you can create an element higher. Is that right? So, protons will stay in the nucleus and the electrons will come out as beta radiations. This means it increases the atomic number by 1 unit and the mass number will not change. Why doesn't the mass number change? Because a neutron and a proton both contribute to the mass number. When a neutron changes to a proton, the total number of neutrons and protons don't change. But the number of neutrons is less by 1. The number of protons is greater by 1. Right? The total number remains the same. The atomic number increases by 1. The mass number remains the same. An example is carbon 14. Carbon, atomic number 6, mass number 14, emits a negative beta. So from now on, we are going to call this beta a negative beta. A beta that carries a negative electric charge, which obviously means sometimes we will be coming across a positive beta. We will see that later. So carbon 14 emits an electron, a negative beta, leaving behind a nucleus of nitrogen that is 1 atomic number higher. And the mass number is the same. Alright. In the same way, an isotope of hydrogen, which is called a tritium, H13, emits an electron, a negative beta, becomes a nucleus of helium, the next higher element, He23. Now, it's good to remember some of these examples and their importance. Now, beta emission can also occur in another form. You see, a negative beta is emitted when a neutron degenerates into a proton and an electron. In a similar way, a proton can degenerate into a neutron and what? A particle that carries a positive charge. Well, that is also possible. So beta emission can also occur by the emission of a positive electron, and we call such an electron a positron. A positron is the opposite of the electron, it has the same mass but positive charge. Now, a proton can split into a neutron and a positron. The neutron will stay back in the nucleus and the positron will be emitted as a positive beta. So a proton degenerates into a neutron and a positron. In this process, it will also emit some massless particles called the neutrino. Well, I'm sure some of you have some idea about these neutrinos. Now, in actual fact, the whole universe is assumed to be full of these particles, massless particles called a neutrino. The universe is actually swarming with neutrinos. But we don't have time to go into that direction at the moment. So look at what can happen in the nucleus. A proton splits into an electron with a positive charge, leaving behind a neutron and another particle, a massless particles called neutrino. Now, as a result of this, a positive beta emission results in Z decreasing by 1 because that nucleus has lost one proton. One proton has become a neutron and a positron. The number of neutrons increased by 1, but the number of protons is decreased by 1. That means a positive beta decay results in the creation of the nucleus of the element one step below the original element, but the mass number remains the same. An example is copper, atomic number 29, mass number 64, emits a positron, a positive beta, leaving behind the nucleus of nickel of atomic number 28, one less than copper, and the same mass number. And in the process, you also have a neutrino emitted in that nuclear reaction. And we can represent that by this nuclear equation. I'm sure you are now familiar with how to write these nuclear equations. Another example is sodium of atomic number 11 and mass number 22 emits a positive beta, becomes a nucleus of neon of atomic number 10 and mass number 22. Now, we talked about two types of radiations, alpha radiations and beta radiations. Now tell me, what are alpha radiations? Alpha radiations are helium nuclei. They're made up of 2 protons and 2 neutrons. The emission of an alpha particle will result in leaving behind the nucleus of an element of atomic number 2 units less and mass number 4 units less. Beta radiations can either be positive electrons or negative electrons. Now remember, most of the beta radiations that we will be discussing will be negative electrons. So unless we specify, we would understand a beta radiation as a negative electron. And as a result of a negative beta, you will produce an element that is one step higher in the periodic table, atomic number 1 higher. Okay, what are gamma radiations? We already know what they are. They are very high energy electromagnetic radiations. Now, gamma radiation or X-rays frequently accompany the emission of alpha and beta radiations. Now remember, the radiations take place in order to create stability in the nucleus. That means throwing away extra energy. You see, the extra energy inside the nucleus is what creates the instability. Throwing away that extra energy. And most of that energy is carried by these emitting particles, alpha, beta, and also these gamma radiations. Well, we have already looked at these pictures already. These gamma radiations are not deflected by electric or magnetic fields. But none of the electromagnetic radiations can be deflected by electric or magnetic fields. These gamma radiations is able to travel many meters in air and many centimeters in human tissue. In fact, it readily penetrates most materials. Well, that brings us to the question of how damaging these radiations are. Alpha radiations are very massive. That means as they go through air, they will be colliding with air molecules. That means they will stop very fast. Beta radiations are very small particles. That means they will not be stopped as readily as alpha particles are. But gamma radiations are very high energy electromagnetic radiations. They can go right through in air for a long distance. Now, radioactive materials that emit gamma radiations and X-rays constitute both external and internal hazard to humans. So when we talk about the hazardous radiations, mostly we are talking about gamma and X radiations, which are very harmful to the human tissues. Well, that doesn't mean the other radiations are not. Alpha and beta are also damaging. Now, dense materials are needed for shielding from gamma radiations. In fact, gamma radiations really cannot be stopped by thick clothing. Now, strong gamma radiations can be stopped only by thick lead sheets. Now, here I have a piece of lead. This can stop most of the gamma radiations. All right. So that takes us to the relative penetration ability of radiations. Which of these radiations have greater penetrating ability? Well, obviously, we know alpha radiations do not penetrate much, but gamma radiations are very highly penetrating. Alpha, the least penetrating form of radiation, can be stopped with a piece of paper or a few inches of air. So they are not very highly penetrating. Now here I have the relative penetration abilities of these materials. Alpha radiations can be stopped by a thin layer of paper. But beta radiations cannot be stopped by a thin layer of paper. They can travel very many meters in air and can be stopped by a sheet of aluminum. In fact, I have a number of materials here which can be used for, I have a box of materials here which can be used for the penetration ability of these. Here I have aluminum that can stop alpha and beta radiations. Well, I have a sheet of aluminum, thick one. Well, depending on the energy carried, you need different thickness. I have different thickness of aluminum to study the penetration abilities of different beta. And of course I have a lead which can stop the gamma radiations. So, higher the energy carried by these radiations, the more difficult to stop them. So, one of the characteristics of these radiations are they have different penetration abilities. Now, what other thing can these radiations do? You see, one of the things that I have not mentioned in the PowerPoint maybe, but I'm going to mention that briefly. When these radiations pass through certain medium like air or any other material, they can actually produce ions. Now, what are ions? An ion is an atom that is missing some electrons. Now, let me see if I can draw a small picture of the atom on the board before I explain. Well, the picture of the atom we have now is that you have a nucleus that is positively charged and electrons in shells or subshells in a region surrounding the nucleus. Now, this is a neutral atom. Now, if some extra energy comes from outside, like in the form of an alpha particle. Suppose an alpha particle whizzes through air and it happens to hit that electron. That electron can be ripped away from the atom. That means this atom now contains one electron less. That means it carries an excess of positive charge. This is now an ion. So an ion is an atom that is missing some electrons. And these electrons can be ripped off the atom by subjecting an element to these radiations. That means these radiations are good ionizing agents. What is an ionizing agent? An ionizing agent is something that generates ions. Now, which of these radiations is a better ionizing agent? Alpha, beta, or gamma? Well, because alpha is massive, along its path, although its path is very limited, along its path, it can knock off electrons from atoms much more readily than other radiations. That means alpha radiations are very effective ionizing agents. Beta radiation also can produce ions, but not as effective as gamma or as alpha. But gamma radiations are very poor ionizing agents. So you can see, as the penetration ability increases, the ionizing ability decreases. Or as the penetration ability decreases, the ionizing ability increases. That is something that you must know of these radiations. All right. We will now look at how to measure these radiations. Is it possible to measure these radiations, to construct a device which can detect and measure these radiations? Well, just like any other measurement that we do, radiations can be measured by the effect they produce. Now, what is the effect that they produce on the medium through which they pass through? One such effect is that they produce ionization. Now, normally, air around us is not a conductor because air doesn't contain free electric charges. But if you can have radiations all around you, if radiation is passed through air, those radiations can create ions. And when ions are generated in air, there are free charges. That means air can be made electrically conducting. You see? So this is one way to detect the presence of radiations. So radiations can be measured, detected, or measured using the effects they produce. Most radiations knock off electrons from atoms in a material producing ions. Now, an ionization counter is a device that can detect and measure ions produced by radiation. So obviously, a radiation detecting device makes use of the ionizing properties of radiation. Radiations also produce flashes or sparks when they fall on phosphorus materials, or fluorescence or phosphorescence. Some radiations, when they fall on certain materials, will result in the emission of light. That is phosphorescence or fluorescence. That property can also be used to detect these radiations. So there are two main properties that we use in detecting and measuring radiations. One is the ionizing ability of these radiations. The second is the fluorescent properties of these materials. Now, most commonly used radiation measuring device uses the property of ionization, and most commonly used measuring device for radiation is the Geiger counter. Now, I have a Geiger counter in here. This is a Geiger counter. Well, let me see if I can put it in a place where light will show on it. A Geiger counter. Now, what is it made of? Well, that is just a picture. That's not very useful. But I have a diagram that shows what a Geiger counter is. Now, a Geiger counter is a tube that contains a certain gas. Now, the tube is metallic, and inside the tube you have a stretched wire. And actually the tube and these wires are two electrodes. Now if you watch in here, this is the metal tube. I think not enough light is falling on it. And if you notice here, the wire in here is connected to the inside wire. So the outer metal cylinder is one electrode and the inner wire is another electrode. That means if you now connect these to a battery or a power supply, if the air or the gas inside is an insulator, then no current will flow, because the current cannot flow from the outside container to the inside wire through the insulating material. But when you allow radiations to pass through here, those radiations will generate ions, and when these ions are generated, this space will become electrically conducting and a current will flow quickly from that wire to the outer electrode, and that current or that pulse can be detected. And that is the principle of the Geiger counter. So here I have the metal cylinder here, and the wire actually does a couple of things. It provides the potential difference between the outer container and the inner wire. That is one wire that goes inside. Also, this part of it is connected to a scalar which will count the number of ionizations that happens. When a radiation goes through, there's a window in here, you can see it here. When a radiation is allowed to enter this window, if it generates an ion, it will be immediately detected and the scalar will count it. Now, here is the scalar that will count that. Let me see if I can show that to you. There is the scalar. It actually has the number in it, and that's the number of radiations that has been detected since I started this lecture. In this room, 218 radiations have been detected. That means there are stray radiations all around us, isn't it? And this is a Geiger counter. This is the counter, and this is the scalar which actually detects and counts and gives you a measure of the radiations. All right? Now, let me see. This is measuring the background radiation. Now what I'm going to do is, I'm going to use a material that is going to enhance radiations. Now this is actually the filament of a lamp. Are you familiar with gas lamps which uses this kind of filaments? Now see what happens when I keep it, well, it's not responding, I think. I have applied a very high voltage. I can actually use the scalar to generate that very high voltage. And you can see it has been counting. And let's see if I can increase the rate by bringing that material. Now you can see the number of counts is increasing tremendously. It is counting the number of radiations. Now, another material that will generate that kind of radiations is actually the porcelain. See the plates that we use for eating? I have a little porcelain material here, and I'm going to keep that. You can see that also generates large amounts of radiations. So a lot of background radiations are around which are generated by a lot of common materials that we use. Well, are these harmful? Well, our body is made to withstand a certain amount of radiations. But when the amount of radiations that our tissues are subjected exceeds that safety limit, that could be dangerous. In fact, radiations can create mutations in your cells, because what these radiations do, they will go and create ionizations and if they hit the nucleus and create changes in the chromosomes, changes or mutations can happen, and that will create in later generations being born without limbs. And if you remember the story of what happened in Chernobyl, a nuclear accident in Russia, children are still born with limbs missing and all kinds of defects because of the mutations that these radiations the people have been subjected to in that area. And those mutations can be passed on from generation to generation. So radiation damage that is done to human beings is actually something that will pass on from generation to generation. And that is one of the things that you must be very clear about and form very, very educated opinions about the presence of radiations, and should we really need materials that generate these kind of radiations around us. Another device that is used for measuring radiations is a handheld, again a Geiger counter. If you look here, there is a Geiger counter built inside. It actually works on battery. The high voltage that is needed between that inner electrode and the outer container can be provided by that battery. And you can see it not only counts, it also produces a sound. It is useful to have an instrument like this which detects the radiation. In fact, some people say a granite counter will produce radiations because of the presence of radon there. So when we had a granite counter put on, my wife asked me about it, and I took this, and there was no effect at all. There's no radiation, there's no extra radiation generated by granite. So to wrap it up, how does a Geiger counter works? When radiation passes through the window, it ionizes some of the gas atoms, producing free electrons. And the presence of these free electrons will make the medium, the gas in between, conducting, and a pulse of electricity pass, and that can be detected, and we can measure the radiations. Well, if radiation can be measured, what is the unit for measuring radiation? Well, one unit for measuring radiations is the number of radiations per second. The number of decays per second, or activity per second, is the most common unit, and that unit is called a becquerel. Of course, a becquerel is the person who discovered radioactivity. 1 decay per second equals 1 becquerel. An older unit is the Curie, of course, after Marie Curie, named after Pierre and Marie Curie. And what's the relation between a becquerel and a Curie? 1 Curie is approximately the activity of 1 gram of radium, and it is equal to 3.7 times 10 to the power of 10 becquerel. If I have 1 gram of radium in here, these devices will go mad, because there will be how many radiations per second? There will be 3.7 times 10 to the power of 10. 37 billion radiations per second. And that is 1 Curie. So 1 Curie is the same as 3.7 times 10 to the power of 10 becquerels. Now the amount of radiation received by human, that is the biological unit of radiation, is in terms of the radiological dose. And radiation dose, that is the biological unit, is called a rem. The natural radiation that people receive a day is about 1 millirem. As I demonstrated, we actually live in a sea of radiations. Our background is filled with radiations. All kinds of sources will produce radiations, and most of it is not very harmful. We get ourselves subjected to 1 millirem of radiations a day. The SI unit for the radiation dose is actually sievert, uppercase S, lowercase v, and 1 rem is 0.01 of a sievert. Now, how do we study the background radiation? I just showed you. And radioactivity is a random phenomenon. There's no way to predict when a radiation will happen or not, because radioactivity is a spontaneous process. Now, if there is a radioactive atom present here, am I sure it will emit a radiation now? No, I'm not sure. It is a random process. Now, I measured the background radiation. Now, the distribution of radiation rate is expected to follow a normal distribution. So what I did is, I measured the background radiation for 42 minutes. Since the class, I cannot make a video as long as that, I used this handheld instrument to measure the radiations. I measured for each minute, and I did it for 42 minutes, and this is the result. There were 25 radiations detected in the first minute, 17 radiations in the second minute, and so on. These are the number of radiations detected in 42 minutes. You can see they are, if you generate numbers at random, they will look like this. In some cases, I got only 5 radiations. In some other cases, I got as high as, what's the maximum number? I think it is 25, is that right? Okay. Now what I did is, I divided them into 7 classes of class width 3, and I obtained this table. In other words, 5 to 7 radiations occurred twice, 8 to 10 radiations occurred 6 times, 11 to 13 occurred 10 times, and so on. Now this is called the frequency table of a distribution like this. This can be used to draw a histogram, and I did draw a histogram. Now on this axis I have the frequency, and I have a 2, 4, 6, 8, 10 and 12, and the first class has a frequency of 2, the second class has a frequency of 6, third class has a frequency of 10, fourth class has a frequency of 11, and fifth, sixth and seventh class. Now look at the distribution. This is called a normal distribution. So we know that radiation or radioactivity is a spontaneous and it is a random process, and it follows a normal distribution. Well, what I have done so far is to give you a picture of what radioactivity is and what are the various types of radiations. And I will spend some more time in the next segment of the video to talk about radioactivity. All right.